Here is an example of airflow in a duct that can be like in a house or anywhere else. Let's say air is flowing in a 9-meter duct, having the cross section of 0.2, like 20 centimeter by 4 centimeter. Just gonna add meter here. Cross section at the rate of, this is the rate of airflow, volumetric rate with the inlet temperature of 80 degrees C. The temperature of the duct wall are at 60 degree, and what it asks is heat transfer rate per unit length and the exit temperature. So we have this duct. This is 0.440 centimeter, 20 centimeter, and there is the air getting in, and what we are air coming in at the 80 degree, so T, M, and I is 80 degrees C. The surface temperature is everywhere constant at 60 degrees C. So the known parameters here, we know Tm and I is going to be 80 degrees C, Ts is 60 degrees C, and the duct area A is 0.4 meter, B is 0.2 meter, and the length of the duct is 9 meter. And I'm just showing the volumetric flow rate with the V dot as 0.2 cubic meter per second. So that's what we know. In terms of assumptions, steady state and no radiation. Okay, to start doing the analysis, first we evaluate the properties. Properties are getting evaluated at average temperature between inlet and outlet, mean temperature, average mean temperature. So first is properties at T average, TMI plus TMO divided by 2. Right now we don't have the exit temperature. Air is coming at 80 degrees C, everywhere 60, so it's going to lose some heat and then going out. So the exit temperature is going to be something between 60 to 80. Since we don't have it, we are going to start with the properties at TMI as a first approximation. And if you look at that one, which is 80 degrees C, the properties of air at the 80 degrees C, K is 0.02953 watt per meter Kelvin, Cp is 1008 joule per kilogram Kelvin, Prandtl number is 0.7154, and density is 0.9994 kilogram per cubic meter. Kinematic viscosity is 2.097 times minus 5 meter square per second. We have a duct. The second thing that we are going to do is we are going to get this flow regime, but for finding the flow regime, we need Reynolds number. Reynolds number needs the velocity, mean velocity, and a representative diameter that we are using this hydrodynamic diameter dH4a divided by pi, 4 times 0.2, 0.4, 0.2 plus 0.4, which is going to be 0.26667 meter, and mean velocity, we have the volumetric flow rate, so U mean is going to be this volumetric flow rate divided by the cross-sectional area, 0.2 cubic meter per second, 0.2 times 0.4. This is cross-sectional area. So this is going to be 2.5 meter per second. That's the air velocity inside this duct. And the next step for Reynolds number, Reynolds at this hydraulic diameter UMDH over nu, 2.5 times 0.2667 divided by nu, which is 2.097 times 10 to power minus 5. And that's going to be 31791.4, which is greater than the critical Reynolds number for turbulent 10,000. So we are in turbulent regime. Another check that we can do here is whether we are in the fully developed or developing region, since nothing has been given in the question. So we evaluate the entry length, which can be roughly estimated hydrodynamic entry length, kind of equivalent to the thermal entry length. Or let's look at the notations. Since we are dealing with the turbulent regime, this is XFD and thermal. These are almost the same, and it's going to be roughly equal to 10D, 10 times the diameter. So it's going to be 10 times 0.2667. So that length is going to be 2.667 meter. And this is much less than L, which is 9 meter. Since it's much less than that, we can assume that, then we assume this is much less than 9, like 2.6, we assume we are in the fully developed regime, or we have a fully developed turbulent flow, let's call that. Fully developed turbulent flow for both hydrodynamic and thermal in the entire duct. That's a fair approximation to give us a Nusselt number for this process. So the next step, I can evaluate the Nusselt number for turbulent flow in a pipe, non-circular pipe, but the equations is the same, dH over K, and that's going to be 0.023 Reynolds number to the power of 8, 0.8, Prandtl to the power of 0.3. So it's going to be 0.23. Reynolds was 31791.4.8, and Prandtl was 754 to the power of 0.3. And that will give us the Nusselt number of 83.165. So HD is going to be 83.165 times the conductivity 0.02953 divided by the hydraulic diameter 2667, which is 9.2 watt meter square Kelvin. The next step, what we do is we evaluate the outlet temperature. This is a duct with a constant temperature, so STMO, we know the ratio of the temperature. TMI is going to be exponential of minus HAS divided by m dot Cp. So m dot is going to be rho volumetric flow rate, V dot. And if I do the replacement, it's going to be exponential of minus h is 9.21 times, and the area is going to be 9 times 2 times 0.2 plus 0.4. Everything divided by density of air is 9994, and velocity was 0.2 times 1008 as a CP. So we are going to get 0.6140. So TMO at the end of the duct is going to be 60 minus 60 minus AD times 0.6104. So the outlet temperature out of the duct is going to be 72.2 degree of C. And then we can evaluate Q, which is H average AS delta T LM, and this LMTD is going to be delta TO minus delta TI log of delta TO by delta TI, which if we do is going to be minus 15.78 degrees C. So Q will be 9.2 H. AS is going to be times 9 times 2 to 0.2, 0.4, and times minus 15.78, and that would be minus 1569.974 watt. So this is going to be the rate of heat transfer from the air to the surrounding media. And a quick note here that if I reevaluate average TM is going to be 80 plus 72.2 divided by 2, that's 70.1608. So we evaluated properties at 80 degrees C at the inlet temperature, and since the difference is much small, this is close enough to the average mean temperature, so we are not going to really do recalculations. The assumptions that we made was fairly close to what's the reality.